Hello students, welcome to the lecture session. In this video, I am going to explain more number of problems and the calculus of variations. In the previous video, I already explained the procedure. Now I am solving some more problems in this. Find the extremal of the function where integral from x1 to x2 y dash square minus y square plus 2y sec x into dx. So let us consider the given function, that is f of x, y dash as y dash square minus y square plus 2y into sec x. So first of all we need to consider what is the Euler's equation, that is dou f by dou y minus d by dx of dou f by dou y dash is equals to 0. Then substitute in dou f by dou y and dou f by dou y dash in the Euler's equation, where f is given by this equation. Let's find out what is dou f by dou y from this equation. So dou f by dou y, if we do for this given equation, what do we get it? That is minus 2y, and 2y sec x is there, where sec x and 2 will be a constant. Therefore we will be getting plus 2 sec x. This is what has been substituted in this equation. Next, we need to find out what is dou f by dou y dash. So the dou f by dou y dash is given by, here y dash term is only one is there, that is y dash square. If we differentiate it, we are getting 2y dash. So that has been substituted in the Euler's equation, which gives us minus 2y plus 2 sec x minus d by dx of 2y dash is equals to 0. Now that is by differentiating this 2y dash, that is d by dx of 2y dash will become y double dash. Therefore after dividing 2, which is common to the equation, then we get minus y plus sec x minus y double dash is 0. Rearranging and multiplying with minus sign, or taking the terms of a function of x alone to one side and the remaining terms to the other side, we get y double dash plus y is equals to secant x. Now for this problem, since it is not a standard form in the right hand side, if we have an exponential or a polynomial or any other like e to the power of or sine and cos we have, then only we can do solve it. But otherwise we have to apply the method of variation of parameters in order to solve this ODE. So let us consider d squared plus 1 of y is equals to secant x, whose auxiliary equation is given by m squared plus 1 is 0. Therefore m will be plus or minus I, and hence we get the complementary function as yc is equals to c1 cos x plus c2 sin x. Next, so we will assume that y is equals to, instead of c1 it will be replaced with a and c2 is replaced with b, and we will consider this to be the solution of ODE, where a and b are functions of x to be determined. If y1 and y2 are the solutions of the homogeneous equation f of d is equals to 0, then we know that a is given by minus integral y2 into phi of x by the Wronskian dx, and b is given by integral y1 phi of x by the Wronskian into dx, where phi of x is the right hand side function, that is sec x, and the Wronskian is given by w is equals to y1 y2 dash minus y2 y1 dash. And here we have y1 is equals to cos x and y2 is equals to sin x. Therefore y1 dash, whose derivative is minus sin x, and y2 dash is equals to cos x. Let us substitute in the Wronskian. So in the Wronskian, if we substitute y1, that is cos x, and y2 dash, that is again cos x, so that it will be cos square, and minus y2 and y1 dash. y1 dash is already minus, so minus of minus it will be plus, and both of them are sine Therefore, it is sine square x. Then what we are getting is, we are getting sine square x plus cos square x, which is equals to 1. Now, minus integral of sin x. Let us substitute in the integral. Then a is equals to, here a is given by minus of integral y2 phi x divided by Wronskian, where the Wronskian is 1, y2 is sin x and phi is sec x into dx, where b is given by integral of y1 into phi of x, which is secant x into dx. So cos x and secant x both are reciprocal to each other, therefore we get as 1 dx, whereas a is sin into sec x, which will be sin divided by cos, therefore it will be tan x into dx. Or the integral of tan x is nothing but minus log of sec x plus k1, or b is equals to x plus k2. So substituting y is equals to a cos x plus b sin x, we get y is equals to minus log sec x plus k1 into cos x plus x plus k2 into sin x, or multiplying k1 cos x plus k2 sin x minus cos x into log sec x plus x into sin x. This is what we are going to get the solution. Next, solve the variational problem delta of integral 0 to 1 x plus y dash square dx under the conditions y of 0 is 1 and y of 1 is 2. So, I is given by integral 0 to 1 with the function. So, delta I is equals to 0 is equivalent to the Euler's equation. Therefore, dou f by dou y minus d by dx of dou f by dou y dash is 0. And we will consider the function f of x y dash is x plus y dash square, and the Euler's equation will become, by calculating what is the dou f by dou y from this equation. If we calculate dou f by dou y in this equation, it is 1, and dou f by dou y dash is equals to 2y dash, which has been substituted in the Euler's equation. So Euler's equation says dou f by dou y, that is 1, and d by minus d by dx of dou f by dou y dash, which is 2y dash, is equals to 0. Therefore, and the derivative of d by dx of 2y dash will become 2y double dash. That 2y double dash is equals to 1, or y double dash is equals to half. But we can write y double dash is d square y by dx square is equals to half. Now, in order to get the solution of this equation, we need to integrate this twice. So, first let us integrate with respect to x. We get dy by dx is equals to x by 2 plus the constant of integration, that is c1. Again, we will integrate this with respect to x. We get y is equals to x square by 4 plus c1x plus c2. Using the conditions y is equals to 1 at x is equals to 0 and y is equals to 2 at x is equals to 1, we get c2 as 1 and c1 as 3 by 4. Hence, we get the solution as y is equals to x square by 2 plus 3 by 4x plus 1, or 4y is equals to x squared plus 3x plus 4. This is the equation we are going to get it. Next problem. Solve the variational problem delta integral of 0 to pi by 2 y square minus y dash square dx is equals to 0 with the initial conditions, that is y of 0 is 0 and y of pi by 2 is 2. So, let us consider f of x y dash is equals to y square minus y dash square, and consider the Euler's equation. It becomes 2y minus d by dx of minus 2y dash, which is equals to 0, or derivative of 2y dash will be y double dash. Hence, after dividing this by 2, we get y double dash plus y is equals to 0. That is, d square plus 1 of y is equals to 0, whose auxiliary equation is m square plus 1 is 0, and it implies m is equals to plus or minus I. When we have an imaginary factor, whose solution will be y1 cos x plus y2 sin c1 cos x plus c2 sin x. And now let us put y is equals to 0 at x is equals to 0. So we will get c1 is equals to 0 and c2 is equals to, here it has to be c1 and c2. c1 cos x and c2 sin x. So y is equals to 0 at x is equals to 0 gives c1 is 0 and c2 also equals to 0. Therefore y is equals to 2 sin x. This is what is the solution we get it. Next problem. Find the extremal of the functional y square minus y dash square minus 2y sin x into dx. Under the end conditions, y of 0 is, y of pi by 2 is 0. Consider the function and the Euler's equation. Then the Euler's equation becomes 2y minus 2 sin x in minus d by dx of minus 2y dash is equals to 0. Or dividing by 2 and rearranging, we get y double dash plus y is equals to sin x, or m squared plus 1 is equals to 0, that is m is equals to plus or minus I. Therefore, yc is equals to c1 cos x plus c2 sin x. Since the right hand side is not equals to 0, which is a non-homogeneous equation, here you can observe there is a sin x. Therefore, we need to find the particular integral, that is yp, that is sin x divided by d squared plus 1. So, in order to find the particular integral, we need to find out d square, we need to replace d square by minus 1, the denominator becomes 0. So, what we need to do is, we have sin x divided by d squared plus 1. So, d square has to be replaced with minus 1 square, that is the coefficient of x in the sin x. So we get minus 1 plus 1, which will be 0 in the denominator. When it is 0 in the denominator, we need to multiply x to the numerator and differentiate this d square plus 1 in the denominator. The derivative of d square will be 2d and derivative of 1 is 0. Hence we are getting 2d in the denominator. So sin x divided by d means the integral of sine, whose integral of sine will be minus cos x. Therefore we are getting minus x cos x divided by 2. So the denominator is free from derivative d operator, and therefore yp is given by minus x cos x divided by 2. Hence the general solution is given by yc plus yp, that is c1 cos x plus c2 sin x minus x cos x divided by 2. Let us call this as equation number 1. Now we use the given conditions to find c1 and c2 present in the equation 1. The conditions what they have given is y of 0 is 0, which implies c1 will be 0, and y of pi by 2 is 0, which implies c2 will be 0. And therefore both the c1 and c2 are 0 in the first equation. Hence we are getting the solution is y is equals to minus x cos x divided by 2, which is the required extremal. Thank you.